Hi, and welcome again to my Physics Online video lecture series. Today's video is going to be a sort of mile-high survey of the laws of thermodynamics. Call them the thermodynamic laws, laws of thermodynamics, whatever you want to call them. I just want to kind of introduce them today. I will make some other videos in the future about these laws that are going into more depth in some of them and maybe going into depth with some related topics, kind of like what I did with Newton's laws earlier, where I introduced Newton's three-fourths laws and then looked at each of the three in turn and also related concepts like mass versus weight and systems of interest, etc. So today starts a series of these that we'll be looking at the thermodynamic laws and some related ideas. Because it's the introduction to these, I'm not going to be especially thorough with any one law. I'm just kind of wanting to state them and maybe give a little synopsis and then move on. There will be additional short videos to focus on the first law and second law in particular, and maybe some discussion of things like thermodynamic work and the Carnot engine and so on. This may also be, at least planned for now, the only one in which I discuss the zeroth and the third law of thermodynamics directly. So what are the thermodynamic laws? How many are there? Well, there's actually 3 plus 1, 4, 3, and a zeroth law. Depends on how you want to cut it. But basically, they're just simply numbered, as are Newton's laws, as the first law, the zeroth law, first law, second law, and third law. And so what does each one basically say? Well, the zeroth law basically gives, in some sense, a definition of temperature and thermal equilibrium. Essentially, it says, let's say you have substances A, B, and C. So you have if A and B are in thermal equilibrium and C and B are in thermal equilibrium, then A and C are also in thermal equilibrium. The first law of thermodynamics, which I'll just label 1 here, first law, is basically energy conservation in thermodynamics. It essentially says that the change in energy, specifically internal energy, for a system is equal to the amount of heat added to the system less the work done by it. In equation form, for what it's worth, the zeroth law might be written as TA equals TB, and TB equals TC implies that TA equals TC. This may not seem very profound, but on the other hand, it actually gives us a way of defining temperature ultimately. The first law usually is written as delta U, that's the internal energy, is equal to Q or H minus work done. So sometimes it's written like this, sometimes it's written like this. The second law of thermodynamics is kind of the odd one out in that it has different ways of being formulated. And those different ways essentially have different names in some sense for what it is that they do or what it is that they say. It's not fair to say it's the catch-all law. It's not. It's very particular. But it defines such things as what's a reversible process, what's the thermal efficiency of a system and what is entropy. Okay, one way of framing that is the sometimes called the engine statement. It basically just says it's impossible for any heat engine to undergo a cyclic process in which it absorbs heat from a reservoir at a single temperature and then converts all the heat completely into mechanical work. There's another statement which is called the refrigerator statement sometimes. It's impossible for any process to have as its sole result the transfer of heat from a cooler to a hotter object. So we cannot convert all absorbed heat into work, especially in particular if we're doing the whole process at a single temperature. We can't undergo a process in which the only result is transferring heat from low temperature to high temperature, meaning you have to have some sort of work input in order to transfer heat from low to high temperature. And last but not least, you cannot undergo a process in which the total entropy of all systems involved are decreased. At least you can't do this without putting some work into the system, and then that work is sort of like lost. So you can decrease the entropy of a particular system, but you have to do that by doing work on the system from the outside. And that generally means that you've increased entropy in that outside system. The third thermodynamic law, after this great mouthful for the second one, basically just says it's not possible to reach the absolute zero temperature. It should be noted here that absolute zero temperature with a quantum mechanics understanding does not necessarily mean no kinetic energy in the system. It just simply means the lowest possible combination of kinetic and potential energy. So that's that. So those are our laws of thermodynamics in overview form, and I'll be making some additional videos in the future to unpack at least some of this. In the meantime, that's your overview, and hopefully you've learned something from it. Thanks for watching, and goodbye.